Welcome, everyone. There's some people coming in from the waiting room just now as it's transferring everyone over. Well, let's get started. My name's Stephen Borg, and I'd love to talk about FHIR Fusion and the analytics on combined clinical and imaging data. I'm from Microsoft, where I am a director in the medical imaging space, but I work very closely with our FHIR team. We're working very tightly with them because we really believe that FHIR and DICOM have data and they're just a match made in heaven. We really want to pull those two things together. So I'm very excited today to be talking to you. I'll be presenting through this. I'd love for people to interrupt with questions. You can send them into the Whova app. Patricia, if you don't mind jumping in, if people have questions midway through, that's fine. But if not, it's okay too. I'll leave time at the end for questions, and then I'll come through and answer any other questions inside the Whova app as well. So welcome, everyone. As I mentioned, my name is Stephen Borg, and I'm over at Microsoft, and I want to talk about a few core things. Why DICOM metadata belongs in FHIR, how we link clinical and medical imaging together, and how we can enhance the data that currently exists in FHIR through something called DICOM structured reporting. And then I'll talk specifically about a solution that I've open sourced that is integrating FHIR and DICOM with DICOMcast. And we'll do a quick demo of some of that exploration. We'll talk about how to get started with DICOMcast, and we'll go into a Q&A. So a few things, FHIR and DICOM. FHIR, clinical data, information-centric workflows, you're all familiar with FHIR. I'm not going to go there. DICOM contains imaging data and really on some imaging-centric workflows. Lots of parts of patients rather than the whole patient. I mean, you might look at an X-ray of just someone's chest, for instance. And then there's two groups. There's DICOM Working Group 20 and HL7 Imaging Integration, and they work together to help combine those two pieces of data. This isn't just an idea that's come out of one or two crazy people. This is throughout industry. We're understanding the need to pull these things together. Here's just a very small list of use cases before we jump into two very specific ways of starting to integrate that data so we can do analytics on those. Support queries that span clinical and imaging data. This is one of the most critical things that we can do. This is find patients with mammograms that are diagnosed with benign breast lumps. Find images of people who've been smokers for the last 10 years, but have had non-cancerous chest lumps. I don't know. I'm just making stuff up as we go along. But all of these things, these are places where we're trying to get data about the patient to develop that cohort, as well as supporting information from the medical imaging space. There's also another big need, and that is to free the clinical data in DICOM. And DICOM has a massive amount of clinical data. We'll talk about that later. But there's findings, there's observations, there's diagnoses, there's all of these things that radiologists look at and they enter into DICOM. But those belong in a place where they can be part of the entire patient record. And that, I believe, is FHIR. We also could do things like provide feedback to radiologists, trigger feedback based on events, add imaging to other hospital systems through that integration. We'll talk about an imaging study. And with that imaging study, we can point right back and open up an image of something. And we can add imaging to reports, those sorts of things as well. So there's a lot of things that we can do here. So this is step one. Step one is simply getting these two systems integrated in some fashion. And that's using imaging study. Now, imaging study is a FHIR resource, and we're going to be able to link FHIR and DICOM through that resource. Here's an example of what that looks like, just grabbed from the FHIR site. But you can see we've got an imaging study with a lot of different types of data elements in it. And it also links to 0 to more series. Now in DICOM, you have studies which break down, there's one study can contain 0 to many series, which contains 0 to many instances. So that cascading effect of these elements. So you have this hierarchical thing inside of an imaging study that points to series and then to instances. And each series can have a performer. So you might have a study of your heart, for instance, that might include both an X-ray and a CT scan. Those would be 2 separate series in a single study. So that particular breakdown is how we've already specified how this integration should happen. And that's brilliant. And that's the most important first step that we need to take. So why do we do that? How do we link it together? I'll show you in a moment, but why do we link that together? It provides this foreign key relationship in FHIR, basically. It's a direct link between FHIR and DICOM. It's linked at the patient level. So a patient in FHIR can now have an imaging study resource and associated observations, we'll get to that in a moment, where we can tie the two together and you can query across and between, back and forth between the two. I think of FHIR as the source of truth for a patient, where DICOM is the supporting player in that game. So predominantly, we're going to be slicing and dicing the patient data up here in FHIR, and then we'll be reaching as appropriate into DICOM to pull that data back up. So we want to enable queries like find patients with mammograms with a diagnosis of benign lumps who live within 50 miles of Kirkland, Washington. Kirkland's my home. So I might want to find that. That's a query I might need to ask, or I might even have more complicated queries that I need to ask. This linking is the foundational step to correlate those. So before we can do any analytics, before we can do any work on this, we really need to be able to correlate these two pieces of data. An imaging resource is the way forward to making that connection. It unlocks just a huge amount of wonderful things. We can trigger actions in either system. I'll give you my favorite example. I was talking with a radiologist and said, I just don't get feedback from customers. I actually have it on another slide. I actually don't get feedback from doctors because I'm a teleradiologist on whether or not my observations, my diagnosis was correct. I'd love it if when I sent back my diagnosis to their DICOM server in the hospital, that when the biopsy came back or when the doctor looked at it and made a final determination, the physician, that I would get some kind of feedback packaged up. Well, that's easy to do, right? If we have this imaging resource link, we know when that radiologist has conducted a report that's part of a structured report that they might provide or an embedded PDF, that's going to come back as a finding and it's going to be dropped in the DICOM service. Through a link to DICOM, that's going to appear back up in FHIR, and we're going to know that that's been completed. Now, once we send, we might do some surgery, remove a lump, send that lump out for biopsy, it comes back, it's negative. That would be very nice if we could package that up and get it back to the teleradiologist, especially as we move to a more remote world where there's this kind of piecework in radiology. We need to be very sure that we're closing that loop and keeping people getting better and better trained through feedback. So that's one thing. We've already talked about adding imaging to other hospital reports, slicing and dicing data like Power BI. If you take your data that's in FHIR and you export it out to Synapse or Bigtable or any other large data slice and dice tool and indexing tool, you're going to be able to then very easily grab all the way through to imaging by linking those two. And then one of my favorites is simply identifying cohorts for research. When you're trying to determine whether someone's a good candidate for research, you need to be able to dive in and understand what, really fiddle with the data until you get the right amount of data. And how people do it today is they fiddle with the data and then they hope they get all the patient IDs, and then they hope when they go over to the DICOM service that they have DICOM files that they can pull. They want to make sure that they have those images of chest x-rays for pneumonia or whatnot. But we have all the diagnoses for pneumonia here, but we don't know if there's chest x-rays associated with those. Well, now we know. And that's that important thing for linking those two things together and help streamline that. Here's two examples. I love both of these. Give me all the medications prescribed with all the CT scan documents and their associated radiology reports for any patient, older than whatever age that has diagnosis of osteosarcoma in the last 2 years. That's a question that you want to, pull out. You might want to find out, is there some correlation with osteosarcoma? And let me see those radiology reports with a particular medication. And you can find that out once that data is tied together. And then the teleradiologist is an example. That's a direct quote from a teleradiologist and who does more than 500 studies each month, and they only get feedback on 3 or 4. Imagine being an engineer, a software delivery expert, or a software developer, and not being able to get feedback from unit tests, from integration tests, from your customers. That's crazy. And this unlocks that. So that type of integration is something that's really critical. But now that's something that's maybe expected or maybe a little bit out of the box. So let's break a little bit further down and talk about pulling clinical data from DICOM structured reports. That's the next step in this journey. First, a brief introduction to an example of a DICOM structured report. And I got to really give a shout out to David Clooney, pixelmed.com. David has done just an amazing work on structured reports. The canonical book is by David Clooney. Back in 2000, he wrote it and talked about what a DICOM structured report is and how these all tie together. This is an example of a report. It is a chest x-ray, the observer is David Clooney, there's a malignant melanoma, this is the history, the findings, multiple masses, best illustration of findings is a link and that points to a particular location, a region of interest on that x-ray. So I want you to remember that best illustration of findings, because I think it's important for later in our discussion. And then some conclusions. We've got, cannonball, metastases, blah, 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 and some diagnosis codes. So this is an example of like what a structured report might look like if it were rendered. So let's dive more deeply into what a structured report is in DICOM. And this may surprise a lot of people. The fact is, this data is stuffed inside a DICOM. So many people look at an imaging study and they think of it as only a bunch of images, the x-rays, the slices in a CT scan, but that's nowhere near all of the things that are inside of DICOM. Inside of DICOM, we have this massive amount of really clinical data captured by radiologists and captured by others that's been dropped into DICOM. And it's actually dropped in as a series or an instance as well. So what's interesting is it falls into that same category. Here's a new instance, and that instance happens to contain this report. So this is an example of what one might look like. It's really just a hierarchy, a completely abstract hierarchy that can hold anything. It's got one top level piece, that's the name. Chest x-ray report in this particular example. And then it's got a node, a link, it's nodes and links, and the link is context. So we have some context here. The context is the physician name. We have additional context, it's the study instance UID, et cetera. So you can see lots of context. Then we have contains, a finding of a mass. This is a code. And then we just keep hierarching down. We can do as much hierarchy as we need to. Now, in practice, because this is completely, it's wide open. Anybody can create a structured report that could be extraordinarily complicated. We sometimes need to lock those down, and I'll get to that in just a moment. But here's an example. It's name value pairs, starts with a root document title, and then specifies all these relationships down the way. And then each one can have, be a parent of many children to an arbitrary depth. So this is a DICOM structured report. So it's nice in that we have this highly structured data. It's not nice in that it's completely flexible into what we can do. So because of that, we've got something you'll see in a moment that'll allow us to constrain these and have like standards for things like radiation dose. So why extract this data? Why pull this data from DICOM structured reports? It unlocks just a vast amount of clinical data. Worldwide, it's just the majority of DICOM studies have doctors, have radiologists who have looked at this data and have made findings, and it remains locked inside this system. It is nowhere near FHIR. So we're building this beautiful FHIR ecosystem that interacts broadly with all of these amazing tools. And you can find observations and diagnostic reports and findings and all of these things in FHIR, except for all of the stuff that the radiologists have worked on. So we need to grab this data, unlock it, and pull that up. And I mentioned it enables those same queries. I can do that query and now find patients with mammograms with diagnosed benign lumps. And I'm repeating it again because it's now pulling the fact that there were benign lumps identified inside of the DICOM file, and we're pulling that out and exposing it. Supports a vast array of capabilities. We can link imaging observations and findings to other patient data, billing and addresses as the things that pop to mind right away, right? We got all of the patient data. Now we can start to correlate these findings and put them into this context, this end-to-end patient record. And I'm going to give you the thing I'm most excited about. Advances in machine learning and AI in the imaging space. If we step outside of medical imaging and we go to imaging proper, photos, the people take, human taken photos. One of the big advances right on that cutting edge today is being able to create precise labeling with imprecise input data. So in other words, we can take data that's been poorly labeled, like, hey, there's a dog in this picture, but we don't know where the dog is in the picture. There's a cat in this other picture. We don't know where the cat is in the other picture. It's just loosely labeled. There's just stuff in there, but no outlines, no circles, no identification of it. And we're able to take those massive quantities of poorly labeled data and train a model that is specific, that's able to highlight where the dog is on the picture and circle that dog. So in other words, advances in AI and ML outside of medical imaging right now, that cutting edge is allowing us to take massive amounts of data that are poorly labeled and translate those into models which are highly specific and very tightly labeled, where you can actually draw region of interest markers around. This could be the next frontier in medical imaging. This AI and ML could be unlocked if we can break out of taking these annotations outside of where they're locked inside of studies, inside of DICOM, pull them out and use those poorly labeled images, which might have, as you saw in that very first example, that pointer that says, here's the best example of that mass, and it pointed to that mass. It's a poorly labeled thing. There could be other masses there as well, but that data is there, and we have already paid to have billions upon billions upon billions of medical images annotated. We do it every single time we walk through a radiology procedure. So we have unreal amounts of already annotated data, but we have to break it out of its constraints where it is today to label it. And it's frankly hard to do so. So that's one of the things I'm most excited about. So where did we go from here? As we looked at the problem, we looked at something like, what do we do with this massive complexity? Do we just try to bite off and bite off everything? And we started with something as a brief hackathon project or a hack project, looking at one thing: radiation dose summary observations. There's a dose summary observation, and we add a profile to FHIR. We're able to specify all of these things, and you see here we have this dose summary. It's part of an imaging study. There's a device associated with it. There's a practitioner, a patient. There's an irradiation event. There's a pregnancy status. There's an indication. These are all observations. There's other forms of things that go into that. For instance, if we take a look here, we're going to see a lot of different types of things and how they map, like the observation study instance UID, looking at body site, looking at device. All of these things map back and forth potentially between FHIR and DICOM. Now you have to do a little bending to make that happen. So in order for DICOM SR to be effective in mapping to FHIR, there's a lot of templates that need to be created and a lot of profiles that need to be supported inside of FHIR. So now let's talk a little bit. Let's put on the brakes and find out how we actually do this. And I'm going to go through this very, very briefly because I don't want to beat this too hard, but I'll show you what we have done with FHIR, DICOM, and DICOMcast. So there's two services. There's the FHIR server for Azure. It's an open source implementation of the industry HL7 FHIR specification. You can easily deploy it into your subscription. You could use either the open source version. There's also a platform as a service version available. I'm just talking about the open source version. And if we look down here, we also have the medical imaging server for DICOM. It's also an open source server that enables DICOM web systems. So in other words, we've got a FHIR service. We've got a DICOM service. Now, how do we tie these two things together? And we do that with something called DICOMcast. And so you'll see DICOMcast is this little piece right here. I'll show you more in just a moment. But the idea is we've got some PACS system, medical imaging system, a vendor neutral archive, something pushing data into the medical imaging server for DICOM. We've got some EMRs, maybe doing some HL7 conversion, who knows, but it's in the Azure API for FHIR. And there's this communication that occurs between them. Now we're able to take this data and move it out and do something with it. And that's really what I think is the most amazing thing now that we pulled this data out, we can now start to process it. And I'm gonna show you a couple things. I'll show you Power BI and I'll demo a little bit on the machine learning side of the house, but that's not it, right? You can pull it into Azure Databricks, Azure Synapse. There's ways to export data to Azure Search, all of these sorts of things. We can use cognitive services, machine learning, et cetera. But this is where those two things connect, and they connect with something called DICOMcast. Now, DICOMcast is relatively simple. There is a simple in concept. Execution, there's a lot of complexity, but very simple to build for at least imaging study. So when something is uploaded to the DICOMcast, we expose something called a change feed. Now, this is where I really wish this could be more standard. The change feed is an API that comes off of our version of the DICOM service. It's not part of the standard, and I really wish it was, because there's no way to just say, hey, give me the last 20 uploaded DICOM things, the instances, and so I can process them. So we had to enable this with something called a change feed, which allows you to say everything that's ever happened in that system. You've got a full record of those changes. So you can replay this, play it, et cetera. And then we have a DICOMcast, and it simply runs. It's just a Linux container that gets deployed anywhere. And that Linux container basically listens, it polls for the changes. When there's a change, it'll go and look inside of FHIR. It'll say, okay, I've got a patient, and here's the patient ID. It'll go to FHIR and query for that patient ID. And it could be the primary patient ID. It could be any of the patient's secondary IDs, et cetera. And if the patient ID matches, first and last name match, et cetera, we're going to come back and say, got it. We have a link, so we can link these two things together. We then reach out, we do a put in a bundle as a transaction, and we merge those FHIR resources, and we push the imaging study and all of the other related things appropriately into the FHIR server. Now, there's configuration options, of course. If you don't find the patient, you may want to create the patient in FHIR. That's totally up to you and how you might want to do that. But then we simply persist that state and process the next batch, and we just move through. It's all open source. You can take a look at it at any time. We find it pretty interesting. I'm gonna switch gears for a moment and now walk into a little bit of a demo. Now, I started with this. Give me all the medications prescribed. But I don't have data for that, and I didn't have data for that. I'm using the SIM hackathon data set. And I'm going to change that question to this one because it's one I can answer. Give me all the medications prescribed with all the mammography imaging and their associated diagnostic reports for any patient older than 54 that's had a breast lump over the last 20 years. Now you're going to see everything is highlighted in colors because these are different slicers. Notice how much slicing and dicing we have to do to get this answer. It's not a trivial query. It's not just something you can just type in as a FHIR query. It's much more complicated than that, or a DICOM query for that matter. So how do we do that? And I'll show you that in the demo. And so in this particular case, I've got an example. This is Power BI, and I'm pulling in the data. You can take a look. I've got some geographic data as well. So like I can take a look at this. You can see I've got 121 patients. I've got 18 studies. I've got a map here that's still evidently loading, but you can see here's all of the imaging studies related to these things. Here's the names of all of the particular patients, and I can filter them out. They might belong to an organization called Organization SIM, and I can filter out and see like where are the SIM people and where do they live, and you can see they live in New England predominantly. They're all down here. But that's not the query that I wanted to run. So I'm going to run over here to make sure that I can deliver on this query. And we've got an age filter. We said, from older than 54. So we can drag this up to 54 or type 54 in there. We'll do 53 in this particular case. You'll see that the study count releases. We got rid of a bunch of our patients. You can see now we have some imaging studies here. And we've lost one of our drugs. Acetaminophen's gone away. So we wanted people with breast lumps older than 54. So let's do a breast lump. Let's search inside that diagnostic reports. Now this is a diagnostic report that is coming from inside of a DICOM service. There's radiology findings. We're saying here's a potential breast lump in a radiology finding, and it's tied together. Here we have Sally Sim at 70, and we can see that the drug that all of the people in this particular cohort, now it's a small data set, this particular cohort, the only drug they're taking is levothyroxine sodium, 50 mcgs once daily. That answers that question. Here's all of the diagnostic reports now available in FHIR. And we have links, of course, to like the surgical specimen. And if we click that surgical specimen, we're going to actually load it up inside of a viewer. Now the viewer, we don't ship a viewer with ours. This is simply OHIF. So we can take a look at it or not. It doesn't really matter. But the idea is that we can then slice and dice that data and show that clearly. I should have fired it up before the demo. But it does give me a chance to get a sip of water while it's pulling down that image. So this is the, this is the surgical specimen from Sim Sally. And you can see it's the specifications for it. And there we go. And you can scroll through it, et cetera. You can of course, you use windowing and everything else. You don't use windowing in this type of view, but you could if you had a different type of view. So that's a way to slice and dice that data and start to do deeper analytics on what we're looking at, what we're looking to do. So that's that slice and dice type thing. As part of a hackathon, we've sliced and diced the data and built data sets, which, here's the cohort, and then sent that cohort through for machine learning efforts. And I'd like to show you a little bit of that as well. So I'm going to move over to a different view. And this is a view of Azure Machine Learning. So inside of Azure Machine Learning, we've got several different things here. Let me just move this out. We've got things like data sets that we can look at, different compute levels. Let me move this out. I'd like to see it a little bit more clearly. And evidently I'm not, how do I pull that? Anyway, you can see here, we've got several different things. We've got notebooks that we can see. We've got automated machine learning that we can run on. We've got designers, a couple other things. We might identify data sets, experiments that we run, modules that are reusable, data processing pipelines that we might need to run through, models. I'll click on this just so we can see some models. I've deployed several different models here along with Smith-Allegramma. You'll see HERT did a bunch. These are all checks dense nets. These are dense nets that we've trained based on the Checkspert data set. And then endpoints. Endpoints are places that we can now call. These are deployed endpoints to do the actual inferencing. And then we've got compute clusters, environments, data stores, et cetera, data labeling and linked services. This is just part of the Azure Machine Learning ecosystem. And it's not a demo of the Azure Machine Learning ecosystem. We really want to be focused instead on the actual notebooks themselves. So I'm going to open up the notebooks, and inside the notebooks, I've got one here, which is the FHIR DICOM Integrated Pathology Predict. And given the time, I want to make sure we have some time for questions, and there's a little bit more I want to cover. I'm going to go through this very, very rapidly. But the idea here is that this is just a Python notebook, and it's a way to integrate FHIR and DICOM for ML inferencing. Now notice I'm doing inferencing. I've trained the model on other data, and I've deployed it now just for inferencing. So I'm just going to quickly blow through this, but there's just all of the stuff like installing it, setting up Torch Vision so we can get it working, registering the model, training the model, getting the FHIR data, deploying it, querying the right data out of it, deploying it, it's again to Azure Container Instance, and lastly, running an example of it. And I'm going to pull this data and just very rapidly, it's going to execute. Whoops, it's going to execute, and we're going to pull an actual X-ray image out and then show it. This is the actual X-ray image that we analyzed. So this is, if we go to FHIR and ask for people who have associated radiology images, we're gonna grab, and some diagnostic stuff, we're gonna grab that image. And then we can see here that like pneumothorax, we test for lots of things, but pneumothorax is the fourth thing. So we've got an 80% confidence of pneumothorax in this particular example. So this is just a place where we can take that and pull it in together. Now, it doesn't matter where you pull it. I'm pulling it into Azure Machine Learning because it's super easy. It's got just some really nice ways to create data sets based on FHIR. I might even based on FHIR and DICOM data. Like here's an example of a data store. This is my DICOM service store. If I click in this, you can see here's my resource group, all of my account name, everything here. It's got all of my data stores basically. And then from data stores, you can create data sets, and data sets are then monitored. So you're looking for trends over time. Like is the data changing? Are you losing fidelity in your model? And here's why, because the input data is changing. You can see here, this is my DICOMcast data set. And that DICOMcast data set simply points to a data set that I've extracted with all of the data. This sits on top of the DICOM service, and it's just all of the data in there. You can see it's loading now. It's not very much. It's only a few gigabytes of data in this particular data set. More than 1.72, more than 4,000 files. But it's just a data set that I can use for machine learning. So point is, as you are extracting this data from FHIR and DICOM, you can start to slice the data in FHIR, pull the data you want, the data that you believe you need to run a machine learning model through. Now go get the data from DICOM, pull that data in, run a machine learning model against it. Additionally, you could create cohorts. You would create cohorts by slicing and dicing your data inside of FHIR, getting the appropriate cohort, and it could be in medical imaging cohort only, and then you can pull that data out in medical imaging and provide it then into pull it out of the medical images out and provide it as a data set that you can then use to train a model. One of the interesting things, and why I find it so compelling to have these two things together, is that when we have these models and the data that we're pulling from FHIR and DICOM, we're able to get the right data together with the medical imaging piece. I'll do just a brief soapbox, but oh my goodness, if you go back and try to pull the data the way most researchers do, who's building AI and ML models, they've got a bunch of data, and then they go into some system, some EHR, and they export the data, and then they take the exported data and they mush it all around until you get a CSV file out of it, and then they do some kind of correlation ID between the two. All of that work could be done directly for us. This is not something that is rocket science. So let's go back to that presentation again. Now that we've finished the demo, and talk a little bit about what's next. We grabbed one, radiation dose, and that just basically just grabs the dosage summary and a few other things that we did as demos. But there's more. There's secondary capture we should be grabbing. There's DICOM seg, DICOM RT and DICOM seg define like outlines around tumors. That's incredible training data that we could have for machine learning. So there's all this metadata markup type stuff that we could potentially grab as well. Down the road, I would love to be able to process the free text radiology notes into structured FHIR data at some point. Think of this. I've shown you structured reporting, but the vast majority of DICOM files in existence today aren't DICOM SR. They're ePDFs, they're embedded PDFs. So what that means is somebody has basically built a document and they've done it graphically. They've taken a screenshot of an image and they put it there. They've done some kind of markup on it. They might have pointed an arrow. They've typed up some notes. All of that is very much free text images that are just slapped on there, sometimes not even pointing to the appropriate image, but just like a screenshot of the image that they believe is important. That's bad. That's really, really unstructured data. I would love to be able to parse that out and get it and be able to put that either in a DICOM structured report, in FHIR as an observation or a finding or a diagnostic report, something in FHIR. But the list goes on and on and on as to what's next. So let's talk then about how you might get started with DICOMcast. And then we'll go into a brief Q&A session. You can spin this all up, less than 3 minutes. It's really quick. This is the link to the GitHub. If you just go to Microsoft Whack DICOM Server, you'll find it eventually, but there's a deploy DICOMcast.md file. And if you click the top one, you have to enter a lot of data. But if you go down to the bottom, it's like, hey, super quick start. Click that. It'll spin up a FHIR server, a DICOM server, and DICOMcast in less than 3 minutes, and you're off and running. I'll show you that in just a moment when we flip back over to a demo. And then if you want to get started with the medical imaging server for DICOM, there's a couple ways. One, you can just deploy it via Docker. That's sometimes the easiest way, just plop it in. Additionally, you can deploy it into Azure, and then it runs as an Azure service, as an app service, and it has all of the related services around it. So either way, you can deploy those two. And I wanted to just leave you with a couple of DICOM SR resources, because I think this is kind of this next step, this next phase as we move into really linking creating this collaborative link between the two places. And then get involved, Working Group 20, the image management group, and fantastic ways to get involved. Reach me in the Whova app. I'm Stephen Borg. You can find me there. You can email me to FHIR Server for Azure at Microsoft.com. I know. I'm a DICOM server person, but this is a great email to reach me at. You can also hit me up on LinkedIn. I'm Stephen Borg. Now, I'm going to come back just a moment to a demo where I'm just going to pop over to our data sets. Not our data sets, but over here, and just show you the DICOM server. This is the DICOMcast overview at the DICOM server. You can check out the overview. You'll see familiar stuff here, but there's some text around how to do it. If you want to look at the concept, this is how you sync the two together, and there's documentation here as well. And lastly, if you want to deploy it, you can go to deploy DICOMcast. It's some documentation for how to deploy it via Docker. I recommend that you don't use this top deployment if you're just experimenting and playing with it. Instead, you come down to here, which for a simplified quick deploy, click the link below to deploy to Azure. This was created by Maura on the DICOM team, and it's just fantastic. I absolutely love it. It's a single click and off you go. So I would highly recommend that particular process. It gives you something that looks just like this, custom deployment, and you just have to provide a couple of details like a SQL admin password and a service name, and then literally you just click the deploy button right here, review and create, and off it'll go, and it'll create that for you in less than 3 minutes. So again, back to PowerPoint, and I will wrap this up with more questions, but I want to point you to to some services that are coming. There's one coming. Ron Vijay from our team is delivering a wonderful talk on analyzing FHIR data using machine learning and analytical tools. He's going to go more deeply. We went into the why on connecting these two and some brief demonstrations. Ron Vijay goes into FHIR proper. He's not going to be doing any DICOM integration piece, but he's going to show you how to take that FHIR data and bring it into ML and analytical tools. Highly recommend that if you're interested in this particular topic. Then I want to talk about some of the other talks from Microsoft that are available. Don't miss some of these. Some, you might have already missed given the timing, but here's that one from Ron Vijay. I highly recommend that. From CDA to FHIR, Responding to COVID-19 by Doug Seven. That's fantastic. Caitlin, I got to see a preview of this presentation. It's meeting the CMS guidelines. It's great. Josh Mandel, as always, is fantastic. Benjamin dives deep with proxy services, and you just don't want to miss his presentations. They're fantastic. Gino, of course. Yeah, if you've seen him before, you know exactly what I'm talking about. Fantastic presenter, really someone you want to listen to. And then there's another Ron Vijay talk right here that is worth seeing. And then Brendan has a talk. It's already passed, but I highly recommend you go back and watch that presentation as well. That's also on some of this reporting piece. And with that, let's jump into questions. And Patricia, I might ask you if you don't mind telling me some of the questions. I don't have my Whova app in front of me, or go off mute and ask questions directly to anybody.
And so yes, this is Patricia. I'm with HL7. I am happy to share a few questions. We have 5 minutes. There are a lot of questions. We'll get to as many as possible. As Stephen mentioned, you can find him in the Whova app or other ways to follow up on the questions. you will also, he can also go back into the session and view the questions after. But this question that we'll go to first was kind of upvoted by the audience, and we'll start with that one. It's from the perspective of an ophthalmology specialty.
Okay.
It says, where do you store the actual image or binary file data within Azure, or does DICOM Web just enable you to point to it?
So we bring it and store it in blob storage behind the scenes. So if you're using the open source toolkit, like I showed you, as the data flows into that open source endpoint, it gets stored in Azure blob storage, or if you prefer, Azure Data Lake storage. So that's the actual location. We store the .dcm files, the .dicom files. That's where they get stored. That's why it's if you're using the open source piece, it's so easy to reach in and use that for machine learning, et cetera, as well, if you need to.
Okay, good.
Sure.
So the next, so there's a tie. Well, these questions are getting upvoted. So the next one we'll address is,
sure,
what would be the difference between the imaging resource you utilize versus the imaging study spec in R4?
I'm having to replay this, and I really wish I had Maura here to talk about this on this talk, because she's done more work with the standards bodies. But as we move towards imaging, there's imaging studies, and the imaging study is going to, please take everything with a grain of salt here. I'm going to give you what my belief is, but you'll want to go out and research this again. So imaging study remains, and it's that pointer to all of those imaging components. So like I mentioned, there's the imaging study, and then it goes down to, the series and the instances, and it really specifies, here's all of those images with pointers to all of them. The imaging resource is a way, it's like it was also, prior to it being called an imaging resource, we thought it might be an imaging document. We thought we might extend the FHIR resource to include a couple things. But as an imaging resource, it's really a pointer to a thing. Like, for instance, if I have an observation in FHIR and I want to point to a specific instance, like one image out of a brain scan that might have 256 or 500 images, I want to just grab this one image and have some annotation about it. That imaging resource points to that one image. So it's a pointer, just like an imaging study, but it's really more focused on calling things out independently.
Okay, good. Okay, and I think we do have time for one more question. This one also was upvoted by the audience. How can Azure API for FHIR image anonymization data be integrated with the medical imaging server for DICOM, which is a common requirement for research or ML?
I love that question. And I love that question so much, because obviously de-identification is absolutely required. And I might be talking out of turn here because we might not have open sourced this yet, but if we haven't yet, it's coming in days. It's the same anonymization engine used for FHIR being extended to work for DICOM. So if you're using the Azure API for FHIR and you're using the anonymization tool and the language and the structure for anonymizing your data in FHIR, that's coming for DICOM as well. So you'll be able to take the DICOM images, the related FHIR images, and do anonymization together. Now, if you have an imaging study and you've already linked, you can, of course, just anonymize the imaging study as it flows out of FHIR without worrying about the DICOM data. But then once you point to the DICOM data, you're getting non-anonymized data. So if you're going to point back, you really need to then anonymize that DICOM data. But thank you for that question. That was just fantastic. And I wish I knew. I should have checked GitHub to find out if it had been open sourced this morning or not, or yesterday or this morning.
So excellent. Well, we're at our time limit here, and there are many other questions in the chat in Whova. Those will be there, and Stephen, you can go in and review, or if anyone wants to reach out directly to Stephen, he has provided you with his contact information, so please feel free. And did want to thank you, Stephen, for this informative and educational presentation. That was excellent.
Thank you very much, Patricia, and I'll be getting back to all the other questions. And if you don't hear from me and you need to, again, reach out on LinkedIn. I'm at linkedin.com/Stephen-Borg.
Excellent.
Easy to find.
Excellent.
Thank you all, and I'm looking forward to talking with you in the future. Bye, everyone.
Thank you. Bye.